Okay, today I'm going to talk about the petroleum systems of the Pacific Northwest. And I want to first talk about the petroleum system essential elements and processes, then talk about the framework of geology in the Pacific Northwest. It's a rather complicated place and has gotten more complicated over the years. Talk about possible source rocks in Oregon and Washington, along with reservoir rocks. Buried history diagram we have from one publication, and occurrences of oil and gas in Oregon and Washington are not numerous, but they are there. And then I want to talk about the working hypothesis as for the origin of the petroleum in the area. But first, why do I include John Armentrout? Well, here John and I are sitting on the beach at the McKenzie River back in 1965 when he and I were at the University of Oregon. And what's important to me about this is that at that time, when we talked about deformation, we always talked about the big push from the southeast or some such thing. Plate tectonics was just, wasn't even around. It didn't become really used until the 70s. And so I think it's important to recognize over the last 60 years how much progress we've made in the geologic community. The other thing is that when John and I retired, we sort of kept our fingers in geology, and he started this Collido group of a bunch of retired geologists and some people still working. And what he wanted to do was work out the sequence stratigraphy of the Collido and Tyee formations in Oregon. It's a big sedimentary package that's of Eocene age and is quite important. And he's put together this all-star team, and I must say they've made some really great progress. So when John asked me to do this, he just inundated me with a lot of literature. So what this discussion today is the literature search. None of this is my original work. It's all from the literature. So first of all, the petroleum system, we talk about the essential elements being the source rock, reservoir rock, seal rock, and overburden rock. Those are the stratigraphic elements that we use. The processes include the trap formation and the generation, migration, and accumulation. And as you know, we put that together on a petroleum system folio sheet, and include the events chart to tie it together temporally. So to get an idea of where we are in terms of, or where we're going, here are the oil and gas occurrences that have been cited in the literature. 3 east of the Cascades and 6 occurrences to the west of the Cascades. So that sort of gives you an idea of where we're going in the discussion. But first, in order to understand Oregon and Washington, you sort of have to look at the framework geology and the evolution of plate tectonics. It's got some accreted terranes in it, and it's one of the classic places for 4-arc evolution architecture. And all of this goes together to make an extremely complicated geologic situation in the Pacific Northwest. If we look at the tectonic terranes, North American continent is on the right, of course, and the Pacific plate is to the left. It's been recognized a long time ago that this west coast is made up of a lot of terranes that have been rafted in. I worked on one of them up in the Cook Inlet, the peninsular terrane, before it was really recognized as a terrane. And halfway through my career up there, it was recognized that Mesozoic section was rafted in. Rangalia was another terrane, Cache Creek. And then there was an important Olympia-Wallowa lineament, which is supposed to be the western boundary of the North American Craton. And then you go into the Blue Mountains and the Klamath as other accreted terranes. So right off the bat, you can see how complicated Oregon and Washington is. Well, the important thing for west of the Cascades is this accretion of the terrain Silesia. And it's a rather important terrain. If any of you have been to Hawaii, you know what a hot spot will do. It creates a volcano, and as the Pacific plate moves over the hot spot, it creates a bunch of volcanoes that trail off to the northwest. Well, here, the hot spot is sitting under a spreading center with a Kula plate on the north and the Farallon plate on the right. And in the background, you can see the Eocene shoreline to which this Silesia terrain becomes accreted around 50 million years ago. And one of the main evidence they have that the hotspot is under a spreading center is the fact that the volcanoes, and in the center here is the Columbia River, get older as you move either to the northwest or to the south. And the youngest ones of 43 million years is in the middle, and it goes all the way out to 62 million years far out. So this spreading center has been working for quite a while. And when it was attached to the Western North America, it pretty much stopped subduction until the North American, or excuse me, the Pacific plate broke off and created a new subductive belt. And all the way through the Eocene and Oligocene, there was relative quiescence in the Pacific Northwest, west of the Cascades, and it allowed for a fairly thick section of Eocene and Oligocene rocks. And you'll notice later on in the talk that the Eocene is a rather important interval for hydrocarbons. One of the important models to keep in mind is the arc trench gap developed by Dickinson and Seeley back in the middle 70s. And it shows the magmatic arc or the volcanoes on the left, and it's being fed by plutons that eventually get uplifted and eroded and dump sediment into the forearc basin. And the structural high, the outer arc ridge, is part or the top of the accretionary prism, which includes a big thick section that is added underneath. It's subthrusted, kind of like a conveyor belt from the trench. And the outer rise is, of course, the oceanic crust that has a thin layer of sediments, and that's a great place for source rocks to be developed. If you look at the forearc in terms of the essential elements of the petroleum system, generally speaking, you get a source rock that's diluted with a lot of sediment. You don't get a good marine source rock being deposited in the forearc. And I sort of think of it as a type 2, 3 source rock, which gives you a lot of gas and condensate, and maybe some black oil. The reservoir rock, and if the pluton isn't unloaded, gives you a lot of lithic material, which breaks down very easily, fills up the pores and the pore throats, so that you don't end up with a really good reservoir rock. The big plus is you get a huge, thick overburden rock, but to counteract that, the geothermal gradient is quite low, very low. And if you look out at the accretionary prism, you can get a type 2 source rock because you're getting an oceanic type of organic matter being deposited. The reservoir rock, though, is usually pretty broken up because it's always being subthrusted. The overburden rock is not quite as thin, but you have a higher geothermal gradient. And we do get oil shows in the subduction belt, and even some gas in some settings, like the Eel River setting in California. One of the really important things that I think is needs to be noticed is this hotspot. Now, shown here is the migration of the hotspot from the west coast, where Silesia terrain was in place, and ending up in Yellowstone. The hotspot didn't move from west to east, but what happened is that the North American craton moved from east to west over the top of the hotspot. And you'll see that I think that the hotspot is important. It's thought to create possibly the Columbia River basalts in the Miocene time, and then the Snake River basalts in late Miocene to Pliocene time. And then, of course, the geothermal hotspot in Yellowstone, which a lot of us recognize as a supervolcano. So here's the setting for the present day Cascade Trench. You have the Pacific Plate being subducted under the Pacific Northwest in Northern California and parts of Canada. And you end up with a four-arc basin, the Willamette-Puget Sound, and then the Cascade Arc, which is an active volcano right now, starts in Northern California and goes all the way up into Canada. And then the back arc of the Columbia Plateau and the Snake River ending up in the Yellowstone area. So here's a cross-section of AA prime where the Cascade Trench is formed. You see the accretionary prism, the Newport, the active Newport four-arc basin, and you can see where the Coast Range is a relatively recent feature. The Willamette Basin, Willamette-Puget Basin, is at what is called a fossil four-arc basin. And then there's the active volcanoes that we see today. And then behind these active volcanoes are the accreted terranes and a highly complex faulted thing overlain by a lot of basalt. And this is the present day street features. And when you look at the two states in terms of a structural sense, you can see a really complicated overprinting of a lot of different structural features. The main Cascade Range goes right from north to south, and west of the Cascades is the four-arc basin setting, present day. And then to the east is the Columbia basalt. You can see a big oroclinal belt that somehow includes the Klamath Mountains, the Blue Mountains and all, and then the Idaho batholith. And then a lot of faulting and heavy black lines there over the Columbia Plateau, which are really the feeder dikes for the plate. So if we take a look at the oil and gas shows relative to these structures, you can see that on the west of the Cascades, the geology looks a lot simpler than it does to the east with all of the basalt and all. So that then is the sort of the framework for the petroleum systems in Oregon and Washington. So let's talk about the possible source rocks. And I don't say potential source rocks because except for the ones east of the Cascades, none of them get over 2.8%, and the HI never gets above 300, which to me, you got to get that to be a good oil source rock. But be that as it may, here's the Eastern Oregon Cretaceous inlier belt. This is the oldest rock where we have oil shows, and it's in the basalt area or the plateau area. And there's what they call the Mitchell inlier near Mitchell, Oregon. You can see the Idaho batholith there on the right in Idaho and the Oregon-Washington border to the north. If you look at this in detail, these were sampled and the Rocky Val data was run on all the samples, and they were able to contour 0.5%, 1%, and 2% line. And 2% is the best source rock we've seen. It's Cretaceous Hudspeth Formation, and it's also thermally mature. So that looks to me like a good pot of active source rock. There is oil in fossils, in basalt vesicles, and in the sediments. So this evidently this source rock has expelled oil into the adjacent sediments. If we look at the modified Van Crevelen diagram of the Rocky Val data, there seems to be two groups, one that appears to be gas prone and the other appears to be oil prone. Though the HI doesn't get much over 400, but these are also thermally mature rocks. So they probably were a fairly good type 2 kerogen when they were immature. So if we look west of the Cascades, there's 3 locations where source rock data has been acquired. The first one we'll look at is the Canyon River area near the Oil City oil field. And then the Skookumchuck Formation, which is part of the Cowlitz Formation, which is Eocene in age. All these are Eocene rocks, with the exception of the Canyon River area. Then there's some source rock data from the Mist Field area. So the Canyon River area was sampled from the Eocene up through the Oligocene. There was really nothing over 1 weight percent, except in a few places. There's one sample above at 2 weight percent, and it's all thermally very, very immature. Now, these are outcrop samples. So, and if anybody's worked in the Pacific Northwest, you know things really weathered badly. So these are, of course, minimum values. The next set of samples comes from the Skookumchuck area around the Centralia coal field. And here there are some coals, not true coals. There's only a couple samples over 50%, but a coaly material does get down as low as 29%. And then another set of samples, and those were all thermally immature as well. Some samples near the Mist gas field. The TOCs are less than 1%, except for one sample. And the RO values are extremely low. So if you look at these last 2 tables on a modified Van Crevelen diagram, you can see that the coals barely make it to 300. And they probably aren't true coals in the sense that they're all, and if 50% is considered a true coal. So possibly some of these coals could expel some gas or maybe some very, very light liquids. All right, so if we look at the reservoir rocks, some examples, we have 3 of these graphs are from the Eocene, the top 2 and the one on the right. And then the Cretaceous one on the left, lower left, is the Hudspeth and Gable Creek, which is from that Cretaceous inlier. And you can see that stippled area, which is what Galloway predict as the typical 4-arc sandstone. So the Cretaceous rocks appear to be typical 4-arc basin sandstones. The other Eocene rocks, the Chickanaught, the Swank, and the Chumstick, they are more typical of a better reservoir rock. They're feldspathic and quartz, and they have very little lithic material except the Chumstick. And to the right there is the Puget group, which is up near Puget Sound, and it seems to have the best source rock, more quartz rich, very low in lithic material, and some feldspar, but not much. And then down in the Eocene, the Tyee is a typical 4-arc basin sandstone, and the Yamhill and the Clarkson Wilson seem to be good feldspathic quartz sandstones. Now the Clarkson Wilson is an important reservoir rock for the Mist field because that's where the gas seems to be or has been recovered. So let's take a look again at the oil and gas occurrences, the liquid now. We just looked at the rock. There's the Rattlesnake Hills gas field, which was discovered in 1913. Then there's the Hohead oil field in the same year, the Watcom gas field in 1930, the Ocean City oil field in 1946, the Cretaceous inlier belt source rock and oil show in 68, which we won't talk about any more than what we've already talked about. Then there's the Mist gas field in 79, the Yakima gas in 81, and the most recent discovery, the Colita gas field, and that's the field that John wanted me to interpret to the extent that I could. Okay, so if we look then at the 2 gas occurrences east of the Cascade Range, the Rattlesnake Hills and the Yakima Pre-Salt. We can take a look at the location of the Rattlesnake Hills east of the Cascade. And it was discovered by drilling a water well by the Conservation Land Investment Company. And it flowed gas at 705 feet from 50 to 500,000 cubic feet a day, which was quite a bit of gas. But it, for some reason, wasn't developed. I guess they wanted the water more than they wanted the gas. But in 1929, they started developing it with 16 wells. They produced 1.3 billion cubic feet of gas from 700 to 1,200 feet at depth, and from a fractured basalt reservoir. From a trap was the asymmetric anticline. And the gas composition with methane and, surprisingly enough to me, some nitrogen. I would love to have the composition of that gas, but unfortunately haven't been able to uncover it, and probably never will because it's so old. If we look at the wells that Shell drilled to the northwest of the Rattlesnake Hills, the first one they drilled was the Yakima, and it was almost a little more than 16,000 feet deep, and they tested gas from 5 zones. They did penetrate 5,000 feet of basalt from an anticline, and the bottom hole temperature was pretty warm, 400 degrees Fahrenheit. The second well, B, shown on the Whiskey Dick anticline, flared gas, and it went almost 15,000 feet deep, but it also penetrated almost 5,000 feet of basalt. Then there was the last one, the 1-9 Burlington, which flared gas and flowed 5,000 to 6,000 cubic feet of gas. And it probably tested oil because evidently it burned black smoke at one point. Now there is, in both of these places, the Rattlesnake, and in this area, as I mentioned before, there is the black tarry oil in sedimentary interbeds and in the basalt vesicles and fossils and geodes. So there's definitely an oil source rock in this area. So now let's move west of the Cascades and start with the oil fields, the Hoe Head. But first, I want to emphasize again that in the Middle Eocene, there was a rather stable shelf, and this stable shelf continued through the Oligocene. And as you remember, the Silesia basement docked in early Eocene time, and the Pacific plate had to break off and start to send its downgoing slab down under this western Oregon. And of course, forearc development didn't get developed real well until the probably late Oligocene, Miocene. But the arc here is considered the Clarno system, which is further east. And each one of these yellow arrows sort of indicates where a delta is that has the different sandstones, the Chigonaut, the Puget, the Cowlitz, Spencer, Bateman, and Colito. And so if we look at the oil samples, the oil fields, it looks like those might be part of the prism, the accreted prism. I can't find any information on what the fields look like, but there was a sample analyzed by GeoMark in 2007, and the oil had about a 28, 29 gravity oil. It was very low in sulfur and very high in pristine phytane, a 5, which sort of an oxic environment, depositional environment, which I attribute to the fact that we're probably looking at terrigenous material, plant pollen, spores, leaf cuticles, things like that. The oil is of moderate thermal maturity, and it's on a deltaic shale. So what we're looking at is probably terrigenous material deposited in a marine environment. And the Ocean City field, which is about 55 miles south, was discovered in 1946. And the only thing I can find out about that is that it produced 12,000 barrels of oil. I assume there is an analysis around it somewhere, but haven't found it yet. At any rate, the Whatcom County gas field again was drilled as water wells, but it did produce gas from 95 different wells. 6 of them recorded some oil from a depth of 170 to 500 feet. And this is from glacial deposits. They think the origin of the oil is from the Puget group, which is further group, and that's Eocene in age. So if it is, there could be a larger accumulation below it. Now, interestingly enough, the gas composition is again methane with some nitrogen. So that's again, nitrogen shows up. Here's the mist gas field, which is further south, and it has 16 producing wells from 13 different pools. It's really a busted up accumulation. It's been interpreted that there's an unconformity right above the field, and I'm told that it's probably a deep water canyon that eroded out just above the Cowlitz Formation. As you remember, the gas is produced in an immature section. It's not a thermally mature area. And it produced from this Clark and Wilson sands, which you've seen on the ternary diagram already. But when you look at the porosity and permeability of this sand, it averages around 25% porosity. And the millidarcies and permeability go from 20 all the way up to 1,500 millidarcy. And the average is probably somewhere around 200 millidarcies. And you can see that the 1 point right there is not in the lithic area. It's pretty much a feldspar quartz rich sandstone and is a pretty good reservoir rock. In terms of the hydrocarbon type, this is definitely a thermogenic gas. The isotopes of carbon for the methane range from 42 to 43. And there's very little carbon dioxide, which is interesting because coal bed gas evidently is very high in carbon dioxide, but there is an awful lot of nitrogen again, anywhere from 2.7 to 5.3%, which I find rather interesting. So this then is the sort of the synopsis of the mist gas field. It was a burial history developed by Armentrout and Suick, just adjacent to the mist field where the depot center is over 15,000 feet. And it looks like using the TTI, time temperature indice concept that Waples developed, the onset of maturity is probably in the Oligocene, and the end is in the somewhere in the Miocene. Now, one of the things that intrigues me is that the thermal maturity here is very low for what you would consider to be forearc basin material. So, I mean, I would expect it to be somewhere in the 15 to 20,000 range, like we do in the Cook Inlet. I mean, it's really deep. It's also very deep in other basins in California that get filled up very, very rapidly. So one of the things that I think has helped this is the migrating hotspot. I think this probably added quite a bit of heat to the overburden and possibly matured the section much sooner than it would if it were strictly a forearc setting. If we look at a cross section from the mist gas field up north, it goes down the east side just in front of the Cascades and down into the Salem, Eugene area. There was one well that was drilled, the 912 Hickey, that recovered gas. And what was interesting to me about it is not the volume of gas, which is not a lot, but they recovered again from the Cowlitz Formation, the same stratigraphic interval of the mist gas field. So it's Eocene, it's an Eocene reservoir as well. And I find it more than a coincidence that all the gas seems to be recovered from the Eocene. So let's take a look at the Kalita gas field in 2000 that was discovered in 2004. If anybody wants to see a wellhead, this is one for the Beaver Hill well. Here's a gas map of the Kalita gas field. The interval gets up to 70 feet thick. There's a lot of coal in the section, and it's subbituminous, so it's definitely thermally immature. The Beaver Hill is right there in the middle to the left. That's the Beaver Hill drill pad. Then there's the Kalita Ranch to the right, and the Davis Flat and Westport and Radio Hill. Those are all drill pads that that we have recovered gas from, or they have recovered gas from. The gas composition is shown on the right. The nitrogen content, again, is very high. It goes from almost 6 to 42%. And the methane is the next biggest, or is the biggest representative of the hydrocarbons, and traces of ethane. So again, if you just looked at this, you might say that, well, maybe this is biogenic, but we find that it's quite thermogenic in nature. So this is a GC of what a gas company would do to find out what the components are in the gas. And you can see the high concentration of nitrogen, very little carbon dioxide, and a lot of methane and a trace of ethane. And what's interesting and what's important in the Sacramento Basin is that the nitrogen is a small molecule and comes out first in the GC. And so you always have to concern yourself whether the nitrogen concentration is a product of migration, or is it a product of the source rock itself? And I can't answer that now. So I took this gas analysis a step further, looking at Tom Lawrenson and Keith Gwenvolden's paper that they published in 1993, where Tom ran around the western United States and sampled everything. And he got some Yellowstone gas, and it plotted in the geothermal, hydrothermal, crystalline portion of the plot. This is a plot with the boundaries set up by Michael Whitaker, and it plots the carbon from methane and the deuterium from methane. And it pretty well marks out thermogenic gas versus bacterial gas from carbonate reduction, or fermentation, acetate fermentation, both of those being biogenic processes. And what's interesting here is that the little stars are the Olympic Peninsula, and that is along the coast, I'm told. And there's a lot of gas seeps, and Tom evidently sampled them, but they're very similar in nature to the Olympic Peninsula gas, or the Yellowstone gas that Tom sampled. So when we look at the same kind of data from the Kalita gas field, there is a sample from the Kalita Ranch, the little square, which is transitional between thermogenic and bacterial, but the rest of them plot very close to the Yellowstone Olympic Peninsula gas samples. Now, is this a coincidence, or is this genetically significant? I think you could go either way. I have not seen a lot of this kind of gas data, so I'm not really in a very good position to really kind of argue one way or the other. But I think it's really kind of interesting that they all plot out in a very, very similar field. So then again, let's go back and sort of summarize the west coast here again. Remember, this is sort of a stable platform. All these gases probably, well, the lower three gases did come from the Eocene. The one from the Whitcomb gas probably seeped up from the Eocene. And then there's the Hohead and the Ocean City, which probably are in the accreted prism or are in another part of the Four-Arc Basin. But this is when the Silesia created a log jam, and the subduction of the Pacific plate really hadn't gotten started in full bore fashion as it is today. Again, I want to sort of reiterate the importance, I think, of this hotspot, not only as a source of heat to generate oil and gas, but also it could very well be contributing some of the crystalline gas to some of the accumulations. And I imagine this is a regional phenomenon in terms of creating a lot of heat. So then want to kind of summarize my observations that I've acquired over the last 3 months, that the oil compositions to me indicate a terraneous rich type 3, type 2, type 3 source rock. The gas composition indicates a very dry thermogenic gas with high nitrogen. The isotopes of carbon and deuterium indicate a contribution from the basement. And the Eocene Oligocene section is probably responsible for both the petroleum system processes of trap formation and generation migration accumulation, and that the post-Oligocene tectonic activity breaks up the migration paths and creates structural havoc as the hotspot migrates toward Yellowstone. So in my own mind, I've come up with this working hypothesis that the source rock and hotspot were responsible for the oil and gas west of the Cascades, and that the different gas and oil source rocks and hotspot are responsible for the petroleum shows east of the Cascades. The hotspot's also responsible probably for the shallow heat source and also the thermal maturity of the source rock, and that really can control the critical moment. So that is sort of a quick overview of what is going on in the Pacific Northwest. So thanks for your attention, and if there's any questions, I'll do my best to answer them. Silence.
Sure, I've got some questions, Les. I guess, are we stopped recording now? Tanvi?